Okay, so this course is on Einstein's general theory of relativity, which remains almost 100 years after it was invented, the best classical theory of gravity we have. Okay, thanks. So the point of this course is manifold. The most basic level, what we want to understand is the theory of gravity. We want to understand the force of gravity. Okay? The force of gravity, we know something about it. Newton's laws of gravitation govern gravitational motion in an approximate sense. A lot of you are very well familiar with the Newtonian theory of gravity. However, Newton's theory of gravity is not quite correct. It was a beautiful theory and has a large range of validity. I mean, doing calculations for rocket motion in the solar system, unless you're interested in real precision, you might well use Newtonian gravity. Okay. But it's not completely correct. It's not completely correct, as has now been seen in many ways from experiment. And its lack of correctness is also clear. Given Einstein's special theory of relativity. If we believe the relativity principle is correct, that already makes the Newtonian theory of gravity sort of already ambiguous. Because, for instance, the law of universal attraction, which tells you that the force between two objects is inversely proportional to the square of the distance between the two objects. You could ask square of the distance in which frame? Or square of the distance, measured along what line of simultaneity? Which is more or less a question. Okay? Then you could also ask, is it true or is it plausible? Is it true? Okay, so this is getting too crowded. What do we do about this? So, yeah, there are a couple of seats in front, so please, 2 people at least come in. I have the suspicion that this is a first-class crowd. So we'll try to avoid moving the class to a bigger room. We'll do it if 3 classes down the road we still have a crunch of space. Okay. Okay. Great. Okay. Yeah. So maybe actually there are very practical things I should have mentioned to you before. Start. So why don't you guys write your name and email address on the sheet, pass it on to Umesh, who, as the classical mechanics people know, is the tutor. Continues to be the tutor for this course. Okay. We'll start an email list to Umesh, and any practical issues we'll discuss over email. By the way, are the lecture timings okay? Okay. This slot and Thursday in the afternoon. Now, there's one small problem. This room may or may not be available on Thursday afternoon. There's some confusion regarding that. If it's not available, we'll send you guys an email telling you where Thursday's is. Okay. Fine. So let me just continue. So the Newtonian theory of gravity, which was approximately correct, sounds at the very least ambiguous given the formulation of Chekhov's special relativity. Okay. For instance, as we said, the question is distance in which frame. Another question is, does it sound really reasonable that you've got a force which is sort of like electromagnetism, but has no analog of magnetism? There is no analog of forces that are affected by the motion of the motion of your masses. None of this sounds like it's likely to be able to be made consistent with the principle of special relativity. Okay, so Einstein was led to search for a better theory of gravitation. A theory of gravitation that would be consistent with the principles of special relativity. For obvious reasons. You know special relativity is correct, you've got experimental evidence for that, it's a nice theoretical framework. You know gravity is correct. Okay, you've got experimental evidence for that, there's experimental evidence for that. Okay, gravity exists. You need a theory that makes the two consistent. And Einstein set about trying to find such a theory. And in doing so, Einstein realized that he had to modify, or maybe more accurately, enlarge the theoretical framework of special relativity and come up with an entirely new theory of gravitation. Not something that takes Newton's laws and tweaks it a bit, but come up with an entirely new theory of gravitation. A theory of gravitation that has that is qualitatively different from Newton's theory in the sense that it has phenomena that are qualitatively new phenomena that are not present in Newton's theory. For instance, in the theory of electromagnetism, which governs the interaction between two charges, there's a force that governs the interaction between two charges, but there are also excitations carried by the force field. There are waves, electromagnetic waves. In Newton's theory of gravity, there's nothing like that. Yes. Force between two objects. The correct theory of gravity that we will study in this course has waves, includes waves just like electromagnetic waves, waves of the force field carrier of gravitation, which are called gravitational waves. Okay? And this is a consequence of Einstein's theory. Okay. So Einstein's theory of gravity modifies Newton's theory in some ways, but also gives you qualitatively new phenomena. Okay. So the first motivation for studying general relativity is to find the correct theory of gravity. Okay. But now, suppose you're a statistical physicist who feels he is unlikely to encounter strong gravitational effects. Maybe you've got, say you're a biophysicist. I don't know, but a physicist is not particularly likely to encounter strong gravitational effects. And you might think, well, that there is a modification of the laws of gravity in slightly strange circumstances is not of great relevance to me. So, for me, why should I study Einstein's theory of relativity? Okay? I personally feel that there is good motivation for every physicist to study Einstein's theory of relativity. And let me tell you why I think so. I think Einstein's theory is a paradigm for good physical theories. It is a theory that, as I mentioned, was invented in order to resolve contradiction between two different elements of known structures of physics. And just by the desire to resolve this contradiction, Einstein, through 10 years of intense and frustrating labor, was eventually led to a new framework that does many things, completely overturns many of the conceptual underpinnings of earlier classical theories of physics. That predicts a wide host of new phenomena. Okay? And that has a great degree of theoretical elegance and beauty. It's a theory with no parameters or no new parameters. Predicts a wide range of new phenomena, has a large amount, makes contact with beautiful mathematics. It's a really beautiful theory. And was invented purely with the desire, starting with the conviction that there must be a way of overcoming the apparent contradiction between two theoretical notions, both of which are known to be grounded in reality. Okay. What I want to emphasize here is that almost, as far as I'm aware, almost uniquely in the history of physics of this high level, the invention of general relativity was guided by experiment in a very limited way. Einstein, of course, knew that there was gravity. He knew that special relativity was gravity. But he wasn't trying to fit the data of a particular experiment or a class of experiments. He was trying to find consistency of theoretical structures. And in doing that, he came upon a new theory of stupendous beauty, but also enormous predictive power, that then has been successfully tested by zillions of experiments. Okay, so it's in the way that it's a theory that sort of that allowed itself to be deduced by very little information, just by following deductive logic, and then allowed the description of a wide variety of physical phenomena, including evolution of the universe. We'll see some of this. Of course, it's really, in some sense, a paradigm for great physics, for great theoretical physics, at least for some of us. It's like a great intellectual victory for humanity to be able to do this. Okay, and for physicists of my inclination, string theorists, it's the inspiration to hope that other great contradictions in physics, meaning the apparent mismatch between quantum mechanics and gravity, for instance, could also lead to beautiful new results that have a large number of experimental predictions, but guided largely by formal, by structural theoretical considerations. Okay, so I feel that. So I said all this because I feel that the study of general relativity is important, both because it's a beautiful theory of nature that describes a wide variety of phenomena in nature, but also as paradigmatic, as the example of perhaps what I think is the best theory of physics. It's the most beautiful theory of physics. Okay, so just as an example of, if you're going to try in your career to make a good theory of physics, hold this up as an example. Okay, if you can do it, if you can smash Einstein, you've done it. Okay, great. So, fine. So now that we've had this introductory spiel, let's start the course. Okay, so I'm going to start the course by reminding you of something we discussed when discussing classical mechanics. Many of you took the classical mechanics course last year, and we started our discussion of classical mechanics by saying that, look, maybe assume that classical motion, the motion of classical particles, this is governed by Lagrangian. And we were also going to assume that this Lagrangian was a function only of positions in velocities, so that the equation of motion would be at most second order time derivatives. Okay? And the first thing we tried to do in that course was to try to understand what Lagrangian governed free motion of a particle. Okay? And in order to try to do that, we assumed the principle of Galilean invariance. That is, that two observers that were related to each other by constant velocities saw the same laws of the equation of motion. We use the same Lagrangian to describe equation of motion, to describe in particular free motion. Okay. So then we said, look, we were interested in Lagrangian to describe the free motion of a particle. Let's say that the coordinates of that particle were x dot. Were x, and x dot is its velocities. Okay. Since we wanted translational invariance for free motion, our Lagrangian had to be a function of x dot. In general, Lagrangian is a function of x and x dot, but translational invariance requires this particular Lagrangian to be a function of x dot. Then we wanted rotational invariance, so this thing was going to be a function of x dot squared. So then we said, well, the most general Lagrangian would be some function of x dot times x dot. Okay? Now, translation invariance, rotational invariance all satisfied with such a Lagrangian. But this leaves a lot of freedom of whole function. F of a real variable, that wasn't good enough. Then we applied the Galilean principle. We wanted this Lagrangian to be invariant up to possible total derivative terms under Galilean boosts. That is, x dot goes to x dot plus constant. Well, you remember, under x dot goes to x dot plus a constant. Okay, let's make this constant infinitesimal to start with. Okay, so let's focus. this Lagrangian transforms how? Well, clearly the change in the Lagrangian, let's look at the change in the action. So delta S, which is equal to integral delta L, is equal to f prime of x dot squared times the change in x dot squared, which is x dot times dot epsilon. Again, this is probably factor. Okay. Now this guy in general is nothing nice. But if f prime of x dot was a constant, then this is a total derivative. That's the dot and x dot. Okay? And that we argued was more or less the only situation in which it would be, for arbitrary motion, would be a total derivative. Okay? So that tells us that f prime of x dot squared had to be a constant. We call the constant was related to what we call the mass of the particle. So that told us that f was a linear function in x dot. The constant part was irrelevant. So we concluded from that the Lagrangian of free motion was m x dot squared by 2. Okay, great. Now in this course, we're going to be interested in motion of things in a relativistic setting. So the first question I'm going to ask is, why is the motion of a free particle what is the Lagrangian for the motion of a free particle within the theory of special relativity? I'm going to address, I reminded you of this because I'm going to address the question in an entirely simple way. Okay, so as before, we want our Lagrangian to be a function only of first derivatives of position, first derivatives with respect to time of position. Okay, so now you might think, well, look, what we're interested in is some sort of Lagrangian, some sort of action which is L dt, okay, which is invariant under Lorentz transformations and depends only on first derivatives in time of the positions. We see this is a very messy way to think of Lagrangians if you're going to start doing Lorentz transformations, because in this Lagrangian, time appears in a special way to start with, just in dt. Okay, and that makes life messy because you want to be able to rotate space and time. So instead of thinking this way, let's try this. Suppose I've got a little particle and it's moving along, and what I'm going to do is parametrize its motion by a false coordinate, by a fake coordinate, let me call it. And instead of thinking of the motion as being governed, as being described by xi as a function of x0, we will think of the motion as being given by x mu as a function of lambda. Okay? Clearly, if I know x mu as a function of lambda, and so it has reasonable properties, it's 1-to-1 in the right way, x0 as a function of lambda, it's a 1-to-1 functions, then I can solve for lambda as a function of x0, and then plug in that solution to obtain xi as a function of x0. So knowing this is equivalent to knowing the motion of the particle in space. What I'm saying is that there's a curve in space-time, and I'm parametrizing that curve by some sort of fake coordinate on the path. Now, while if I knew this, I could find xi as a function of x0, this is not inverted. I cannot find this function from knowing xi as a function of x0, because this function is a function of some fake parameter about which I've said nothing. Okay? You choose one parameter to parameterize the path, I choose another single valued function of your parameter that equally well parameterizes the path. Okay? So, in introducing this function has a large degree of ambiguity in it. It takes the same physical curve in space-time and parameterizes it in different ways. Different choices of parameter could amount to different parameterization by this fake parameter. They will keep us in mind. Nonetheless, what we're going to do is this. We're going to imagine that we have such a description of this particle, and what we'll do is instead of we take this Lagrangian L dt, and what we will then do is to write this as integral L dt by d lambda. since this lambda has nothing to do with Lorentz transformations, the requirement of Lorentz invariance of this action here is just the requirement that this object here is Lorentz invariant. Okay? So let me call this guy L tilde, which was L d by d lambda. Okay? This quantity, okay, I'm going to try to make Lorentz invariant. Now, well, like before, I'm going to try to make some function of dx mu, this time by d lambda. It's going to be Lorentz invariant. Okay? So what function of dx mu by d? No x's are allowed because of translation invariance. Once again, we've got only dx mu by d lambda in our hands. What function of dx mu by d lambda is Lorentz invariant? But that's clear. It's eta mu nu dx mu by d lambda. Dx mu by d lambda. This is a nice Lorentz invariant object. And it's the only Lorentz invariant object that you can build out of dx mu by d lambda. Okay. Yes?
So is it possible that we can find a function which differs by a total derivative?
Function of what?
This L dt d lambda.
Yes.
It might change by a total derivative but it's not possible.
Yeah, we will allow that possibility. At the moment I'm saying that wherever N is, it's, oh, you mean that it's not invariant.
It's not.
But changes under total derivatives. Good. Yes. Good question. Okay, I need to think about it. It's a good question. It's a good question. As Anshant points out, what I'm assuming here is that the Lagrangian itself is invariant under total derivatives. I suppose I made that same assumption here by finding that the Lagrangian was invariant under rotations. Okay. So I should do better if I want to address this. Let me think about that. Right? Okay. Let's make the assumption, however, that we're looking for an object that at the moment is invariant. Okay, excellent. So we've got this object here. So now we want some function of this. But remember that this function should introduce dependence on this fake parameter we could talk about. It should have the property that the action is invariant if you take lambda as some function of lambda. But the action has L tilde multiplied by d lambda. Okay? The only way that this thing is going to be invariant is if the homogeneity of this function in lambda is -1. Because then the change of variables will cancel between the change of measure of d lambda and the chain rule in d lambda. Okay? -1 in lambda, which means which means half in this object. Okay? So basically we led to the Lagrangian L is equal to -m, let's say, square root of minus dx mu by d lambda dx nu by d lambda eta mu nu d lambda. With precisely the square root, the change of variables that we, if you change lambda to some function of lambda, the change of variables from here will cancel what you get from the measure change. Because you've got two factors in the denominator and there's a square root. Assuming that everything is 1. Okay? Is this clear? So, just by the demand of Lorentz invariance and basic general principles, we're led sort of inevitably to this action, apart from Harshan's question, allowing for total derivatives, which I need to think about. Okay, excellent. Okay. I've put a minus sign inside the bracket. Okay, good. because I should have said this, in my in this course, I think we will. The problem is Landau evolutions uses the opposite convention. Okay, what then? Maybe I should just immediately switch to Landau evolutions. Yeah. Okay. So let me. So minus sign or not depends on what my interpretation is. Okay. So let me once and for all bite the bullet and adopt Landau evolutions stupid convention. Being 1 minus 1 minus 1. Landau evolutions classical theory of fields will be the main text for the first part of the course. I should have said the course is planned in the following fashion. We're going to have about a couple of months on basic general relativity, which is roughly pages 250 to the end of this book. Okay, and I'm hoping we will have time for 3 weeks on black hole physics and 3 weeks on cosmology. Okay, so the idea of the course is to cover basic general relativity and then talk about black hole physics, which is very exciting. Cosmology is also very exciting. Okay, the two main current research applications of general relativity. Okay, fine. So now suppose we do this, then we would get a plus, because a particle moves along some sort of time-like trajectory. Okay, now you don't want to take square root of the negative one. Okay, with this convention of eta, this guy is just positive. And then when we still need the minus. We need this minus sign to. Okay, how do I identify this parameter here? I identify this parameter in the following way. Okay, let me do that. See, this Lagrangian here has been written in terms of d lambda. I can choose lambda to be anything I want. As one example, I could choose lambda to be time. Okay, so in the case lambda is equal to x naught. Hi Sandeep. Hi Sandeep, I'm teaching a course at the moment, so I'm working on it. Ananya will be going to make Sandana. Could you be able to meet her in the talking about 5 minutes? Okay, fine. Okay, so suppose I choose a lambda to be x naught, then my Lagrangian becomes minus m, and let's write it out really explicitly. This is dt, x naught is 16. And this thing here becomes 1. That's the dx naught by d lambda squared minus xi dot squared. Of course, I'm working with the speed of light. Okay, now I take this guy and I expand it in small velocity unit. This becomes L is equal to minus m plus m by 2x I dot squared, which is the non-relativistic Lagrangian. The Lagrangian for non-relativistic. Sorry? Yes, no. I've got a name overall. Well, if there's a name overall, it will appear everywhere. There are two ways. Here. Minus m integral dt. This is the one. I take the square root. And square root of 1 minus a is 1 minus a squared by 2. Okay? This term is constant. It's total. I mean, you throw it away. It does nothing to the equation of motion. This term gives you the non-relativistic Lagrangian. So I identify the factor N here to make contact with the non-relativistic Lagrangian. Okay, so that would be the same mass that we refer to as mass in non-relativistic physics. Right. So now I'm through. I have the Lagrangian for for the motion of the part. Just one second. My son is picking up. One. Make sure. I'll pick up. describes the motion of a free particle in relativistic physics. Okay. Now, I'm going to motivate the introduction of our study of general relativity by the following consideration. Look, while special relativity is a beautiful framework for physics, there was always something a little unsatisfying about special relativity, and that was the arbitrary specification of which frame is an inertial frame. You start in special relativity by saying there exist these special frames, inertial frames. Once you know one frame is inertial, others are those that are related to it by boost. But these frames are somehow different from all other frames of physics. They're different from accelerated frames. Okay? The laws of physics take one form in inertial frames and other forms in other frames of reference. Okay? This seems somehow a little odd. Who decides which is the inertial frame? Okay? This question will not get partly but not completely cleared up in the study of general relativity, as we'll see. But it's this discomfort that might lead you to ask, look, suppose I wasn't using coordinate x mu, appropriate to an inertial frame. Suppose I was using arbitrary coordinates to describe the motion of a free particle in special relativity. Then what would the form of my Lagrangian be? Okay? Now, Lagrangian mechanics is very well suited to answering such questions because it's very easy to make changes of variables within Lagrangian. You just make the substitution. Okay? So let's make the substitution. So, suppose I have x mu, which are the coordinates in some inertial frame, are some arbitrary functions of some new coordinates which I call y. Okay? Now what happens to this Lagrangian? Well, clearly you get the following. You get the Lagrangian goes to minus n integral g alpha beta dy alpha by beta dy beta by d lambda. Where g alpha beta is equal to tau mu dx mu by dy alpha dx mu by okay, I get this by using the chain rule of differentiation. But right. Yeah, these are all partial derivatives under the condition that x mu is differentiated with respect to y alpha with all other y's kept constant. Okay, and I get this by using the chain rule of differentiation, substituting dx mu by d lambda in terms of the derivatives dy mu by d lambda by using the chain rule. Is this clear? Okay, so this is the Lagrangian now for relativistic motion in an arbitrary coordinate system. This is already useful, by the way. Suppose we were just doing special relativity and you wanted to understand how to work in a coordinate system adapted to your problem. Some rotating coordinates, something like that. This is your Lagrangian in that coordinate system, and you can derive the equations of motion straight away in those coordinates without having to ever rely on inertial coordinates. Now, looking at this Lagrangian, you might think the following. You might think, wow, this is quite a nice Lagrangian. And you might wonder, look, this Lagrangian depends on this object G alpha beta. It's a symmetric, this object is clearly symmetric because when it multiplies is symmetric, so any anti-symmetric makes it 0. But it's also symmetric from definition. Because this is symmetric, this is symmetric. Okay? And you might wonder, look, by doing all these coordinates, by choosing y alphas in an arbitrary way, can I generate all possible symmetric G alpha betas? Okay, so this object at any given point in space-time is a matrix. It's a 4x4 matrix. Its indices run over 4 variables here and here. And while eta was a constant, it didn't depend on where you were in space-time. This object depends on where you are in space-time, because these derivatives depend on where you are in space-time. Okay? Because dx alpha by dy mu is a function of what? So this object here is what's called a symmetric two-tensor. It's a tensor field. Okay? And you might wonder, can I generate all possible tensor fields by doing coordinate transformations on eta? If so, this is a better way to state what the laws of physics are, and because it doesn't make we come to that. But let's first address this question. So, can somebody tell me? Can one make every G alpha beta by starting from eta and doing this coordinate transformation? No, you cannot. That's correct. Tell me why not.
Because it's flat.
Flat. Now you guys are using knowledge that we're not supposed to have. It's true. It's because it's flat. But it's something more simple. If you're looking at this problem for the first time, you've never heard of flatness or curvatures. It's still obvious that you can't. Right? What? You're still using knowledge that we don't have. I'm sorry, I mean, it's fine to use knowledge that we don't have yet. But there's something very simple to say. Okay? The very simple thing to say is that, look, what you're asking is, can you make an arbitrary set of 10 functions? Just count. How many functions are there in G alpha? We're counting how many components there are in the symmetric matrix. We've got a 4x4 symmetric matrix that has 10 components. Can everyone do that counting? Can somebody tell me what formula gives 10 out from 4x4? Or what would you suppose better still? Have this been a D cross D matrix, how many components would that be? D, right, n plus 1. D into D plus 1 by 2. Okay. And if we plug 4, that's 4 into 5 by 2, so that's 10. So we've got 10 functions in 4 dimensions. We're trying to generate arbitrary sets of 10 functions, starting from a known tensor, and multiplying by objects built out of 4 functions. We just don't have enough degrees of freedom. You can't make arbitrary sets of 10 functions using 4 arbitrary functions. Okay? So this construction doesn't give you an arbitrary metric. It doesn't give you an arbitrary G alpha beta function. Why? It gives you a 4 parameter set of the 10 parameter set of possibilities. This is inaccurately said because we actually talking about functions. So it gives you a 4 into infinity parameter set out of 10 into infinity possibilities. Mathematicians tell you 4 into infinity is same as 10 into infinity. It's just not true. Okay. Fine. So, fine. So, this Lagrangian that we've written here cannot, it's not like there is no coordinate system. You cannot, if I give you an arbitrary G alpha beta, you will never be able to find a coordinate system in which the original Lagrangian, this guy, takes this form. Okay. But, having a Lagrangian of this form, you might wonder, could it be that there is a role in physics? Okay, could it be that there is a role in physics for this Lagrangian? For arbitrary functions of G alpha. Although from special relativity, we only get this 4 parameters. Could it be that somehow, that's because special relativity has not got everything right? Could it be that there's a role in physics for particle motions governed by its Lagrangian for arbitrary functions G alpha beta? Now you see, special relativity may not have got everything right, but it's really got a lot of things right. Okay? So if you look at small deviations from those metrics that can be formed from eta, you'll get a small change to the equations of motion of free motion from special relativity. Now, small change to an equation of motion means is what we think of as a small force. Okay? So, if there is a role in physics for motions of this particle in an arbitrary g alpha beta, this must be associated with what in special relativistic language we thought of as a force. Now, what can we say? What can we say about the force in question? So what's the proposal? The at the moment crazy suggestion is the following. Suppose that one of the forces of nature can be described by just allowing g alpha beta to be an arbitrary function, not necessarily a function transformed by coordinate transforms from flat space. Now, this sounds crazy. It sounds like there's no motivation so far. But let's take this thought a little further. Suppose it were true. What can we say about this force? Now look, why you cannot get arbitrary functions g alpha beta? Why we cannot get arbitrary functions g alpha beta by doing these coordinate changes? Something we will prove once we start doing this, coordinate transformations a little better, is that at any given point in space, you can always take an arbitrary g alpha beta and make a coordinate transform to bring it to eta immediately, or vice versa. And at one point, you can make any g alpha beta you want. Actually, you can make any g alpha beta and any derivative. First derivative. This is something we'll prove as we go. Okay. The first statement is also, by the way, basically obvious. It's the statement that you use a coordinate. I'll prove it later. But the point is that you can use a coordinate transformation to diagonalize this, and then this coordinate transformation isn't quite a similarity transformation. It's M transpose. So you can use that to set the eigenvalues to whatever the likes. Okay, this is actually very similar to something we did in diagonalizing quadratic Lagrangians in classical mechanics. But we'll prove this. Okay. So, but just not to distract. Let me just assert it. Okay. At any given point in space, we can produce any g alpha beta we want from eta by an appropriate coordinate transform. Okay? And actually it's true that even the first derivative can be set in by an appropriate coordinate transform. Now what does that mean? You see, the fact then that g cannot be set to eta everywhere by coordinate transform. Were we able to set g to eta everywhere, we would be back to free motion in special relativity, so we'd be setting the force to 0. Okay? So the fact that we cannot set g to 0 everywhere is something that we need to go beyond local to see. Locally, you can always set g to eta at a point and including the first derivative. Okay? Now, setting g to eta by coordinate transform. Let's finish the argument. Setting g to eta by coordinate transform. Coordinate transform is moving to a frame of reference. And you choose coordinates in which you are setting that are, say, accelerated compared to the original coordinates. So what you're saying is that this force, whatever it is a force that locally can always be set to 0 in a little region. Okay? Can be set to 0 by moving to the right frame. Right? By moving to the right coordinates, it is the right frame. So, it is a force that in a little region of space-time looks like no force in the right frame, or in other words, in an arbitrary frame, looks like a pseudo force from and being in a non-inertial frame. Now you can look around and ask, okay, now, these sound like a lot of words, but you can ask, is there a consequence of these words? The consequence of that's the immediate consequence of these words. The immediate consequence is that, look, these pseudo forces, by being frame change things, don't care about which particle you're looking at. So if you have 7 different particles, okay, they all were initially in identical motion. Then the force of them due to these frame change pseudo forces is always the same, independent of any other properties of these particles, independent of their charge, independent of the magnetic dipole moment. Okay? So, if it's true that there is a role in nature for making G alpha beta arbitrary, that is, if it's true that there is some force that is described by making G alpha beta arbitrary, this force must obey the principle of equivalence. The principle of equivalence, which states that in a little local region, you can choose coordinates to get rid of forces, and these coordinates are not particle by particle. You can choose coordinates for all particles in that region to get rid of all forces. Okay? So that if it's true that this G alpha beta is mediating certain force, then this force obeys this beautiful principle that it is possible locally to move to a coordinate system in which it looks like there are no forces. Okay? This is Einstein's famous principle of equivalence. And now you can look around in nature and ask, are there any forces that obey this principle of equivalence? This, in particular, implies that two particles setting out with identical initial conditions follow identical trajectories irrespective of all particle properties. There is one force of nature that has this property. It's gravitation. Okay? Two particles, Galileo's famous thing, right? You take a vacuum, you take a feather, you take the stalk, drop them together, they fall at the same time. Electromagnetism doesn't have this property. If you take an electron and a positron, it behaves differently. It's different. You can't, if you move to a coordinate system in which the force is gauged away, it's taken away from the electron, the positron will be moving in the opposite way. Okay? So electromagnetism doesn't have a property. No other fundamental force law that we know of has this property. But gravitation does. Okay, so if our crazy idea is correct, then we can get some sort of force of nature by making this G alpha beta an arbitrary function. Then the only candidate force that we could be getting as a force of nature is the force of gravity. Okay, fantastic. So, we're now going to, of course I wouldn't be saying all this at the beginning of a semester-long course if it wasn't true. It's true. The correct formulation of the theory of gravity is completely different from the way the correct formulation as far as we know it today of theory of gravity is in terms that are completely different from Newton's constants. The basic objects of this theory are metric. This quantity that we're going to call a metric, G alpha beta. G alpha beta in special relativity, in special coordinates, is this object. In arbitrary coordinates, special relativity, it is anything that you can get from this object by coordinate transformations. But in general relativity, it is an absolutely free function of coordinates. We have 10 absolutely free functions of our with no constraint that they be gaugeable, that they be coordinate transformable to this form. And when you've got metrics, it cannot be coordinate transformed to eta. In such situations, particles moving around experience what a special relativist would call a force, and that force will be the force of gravity. Okay? So, this is what we're going to try to do. We're going to make a theory of gravity. Okay. We're going to make a theory of gravity in which there are two components. The first component is of our theory is how. Okay. So the first claim is that there are new fields in our theory that nobody had ever thought of before. These new fields, these are new dynamical fields in this theory. They are these G alpha vectors. G just like in electromagnetism, there are new fields aiming. Okay, there are new dynamical fields that have not been properly appreciated for Maxwell. In gravity, there are new fields G alpha beta. Okay, now just like in electromagnetism, moving charges around, what the charges are doing, what other things are doing, determines what A nu will do. We need an equivalent rule for that. For the rule for what is the rules of dynamics for the new field G alpha beta. I'll try to find this rule will take much of our effort in the next few weeks. Okay? We need a Lagrangian for the metric. Okay? However, once we have this Lagrangian, once we have a particular metric, test particles moving around in it experience an effective force. And the rule for that effective force we've already determined, at least as far as test particles go. This is our Lagrangian. Okay? So what we're going to do now, in the next couple of lectures is, well, firstly I'm going to take now, I'm going to take a couple of lecture interlude on talking about the mathematics of coordinate transforms that we will need through the rest of this course. And then we will talk about the properties of particle motions coming from such a Lagrangian. Okay? This we can do without even knowing the rules for what the evolution of the metric is. Okay? And then about 4 lectures from now, let's say, we will start getting to the real part of general relativity, which is the theory of the dynamics of G alpha. Okay? So now I'm going to pause for questions, and after those are over, we'll start talking about the mathematics of coordinate transforms. Okay, now just why I'm interested in the mathematics of coordinate transforms? I should emphasize this. You see, there are two basic ideas that go into general relativity at a basic physical level. Okay? One is this principle of equivalence, that we're trying to write down a force which can locally be transformed away by going to an appropriate coordinate system on all particles simultaneously. Okay? That's inherent to the idea that forces are obtained just by taking this Lagrangian and making G alpha. But the second thing, the thing that has motivated all of this, we started this whole discussion by saying, look, this business about working with coordinates and inertial frames is a little artificial. Let's free ourselves from this. Okay? So the second basic principle that, is in practical life more operational and more, the heart of what you're doing all the time, is the principle of coordinate invariance. That is, we are going to try to write down a Lagrangian for our system that is correct in every coordinate system. Okay? We're not going to single out some coordinates as special because they are inertial. Or some coordinates are special because we like them for some other reason. Our Lagrangian, we will demand, is correct in every coordinate system. Now, particular coordinates may be well suited to studying particular problems of physics, the universal system. But that's another matter. The form of the Lagrangian will not discriminate, will not specify, will not say this is the Lagrangian in this coordinate system, and it's more complicated than some other coordinate system. As far as the basic equations of dynamics go, we will be completely democratic in coordinate systems. Okay? That is the second basic idea underlying this whole way of thinking. It's the principle of coordinate invariance. Now, because this is what we want to do. We want to try to write down some sort of Lagrangian that's completely coordinate invariant. It's clear that before we start doing physics, we need to take a mathematical interlude. Okay? We need to understand how to make coordinate transformations well. Okay? So that's what we're going to be doing starting now after questions. I'm sorry, I stopped you for your further questions.
I think it's clear. Actually, I was confusing it. G alpha with the can be entirely arbitrary.
Completely.
Actually, I was thinking that fine-tuning of capital G, we have this constant will affect it.
No, this is an independent question. Okay, other questions about this? Okay, is the idea of what we're trying to do, the motivation for what we're trying to do, is that clear? Okay, great. So, now let us, so we'll come back to this Lagrangian in a couple of lectures. We'll come back to this Lagrangian in a couple of lectures and study its dynamics in some detail. Okay? But before we do that, just because the objects that will enter in the study of the dynamics from this Lagrangian, there's lots to say about these objects. Okay? We're going to do some mathematics. And the mathematics we're going to do is the mathematics of coordinate transforms. Okay? But the one thing I want to say about this Lagrangian before we forget is that, look, we wrote down the Lagrangian this way. Now you see these two factors, square root d lambda, really cancel between these two. So now the way of writing this Lagrangian is integral square root of g alpha beta dx alpha dx or dy by beta without talking about a lambda at all. Just of course satisfying because we know that changes a variable in lambda cancel. That's all. That was the principle that determined that something. Okay, now this quantity in general relativity has a name. In special relativity has a name. Is the textbook side? Some people call it the interval. It's the invariant distance in special relativity. Okay, and this quantity, this little quantity that, more physically maybe it is the proper time. The square root of this is the proper time experienced by an observer who's moving along this trajectory, a particular trajectory. Okay, now we're going to think of this g alpha beta, here, as determining distances on a space-time manifold. Okay, so this quantity here, the square root of this quantity, I'm going to call a length. Okay, it's just a name. But the important thing is that this quantity itself is coordinate invariant. By definition. Okay, when we started the eta mu nu dx mu dx. And then we changed both things, so the quantity didn't change. Right? Let me remind you. We started with eta mu nu dx mu dx mu. Let's call this ds squared. And then what we did is to say that this is eta mu nu del x mu by del y alpha del x mu by del y beta dx dy alpha dy beta is equal to, and this, whatever it was, we call g alpha beta dy alpha dy beta. Okay, so if I put y's here and use g here, g appropriate to y, I get the same quantity as putting x's here and putting the g appropriate to x. Okay? So this quantity is an invariant, coordinate invariant quantity, okay? Which we will refer to just as a name as the distance square. Because in many senses it will be analogous to a distance in Euclidean physics. Okay? And this quantity we will call the metric. The thing that determines distances. Yes.
Sorry for interrupting. Is there any constraint on g alpha beta to be something like having negative determinant or anything?
Yes.
Because it can be, say, delta alpha beta.
Yes. G alpha beta, as we will see as we go along, will have, you see, locally, you can always diagonalize G alpha beta. And this diagonal object has to have one negative and three positives. When you bring it to diagonal form, it should one value should be negative, one of the diagonal elements should be negative, and the other three positive. Okay, in particular the determinants. We will study this as we go. Is this right? That's a good question. Okay, right. So now we turn to the study of the mathematics of coordinate transforms. So, this is the same as the mathematics, or some part of the mathematics of manifolds in mathematics. Okay? what we are interested in is space-time. We call this, a mathematician might call space-time a manifold. Okay, we don't give too much about that. And we got some coordinates on our manifold. Let's say our coordinates x. Now, your friend doesn't like x mu coordinates. He decides to use y mu coordinates, such that x mu is some known function of y. Okay? And what we want to do is to relate the description of all quantities of interest that you use to the description of all quantities of interest that your friend uses. That is our program. We want to understand how to transform between things said in the x coordinate and things said in the y. So let's start really simple. First, suppose you've got a function on your x. So you've got a function that you call phi of x. Now, what is phi of x? It's a number associated to any point on your manifold. Given position x, you determine a number. Okay. Now your friend also wants to describe the same function to the same point in space-time, the same physical point in space-time. He wants to associate the same number. Now, is he going to use the same function of his variables y? Yes or no? No. No. See, because I mean, if so let's say that my function is let's say for simplicity is one coordinate. So my function phi is equal to x, and by x was equal to y squared. Clearly, your friend's function is y squared. As a function of one variable, it's a different function. Looks like a parabola rather than a straight line. Okay. So the first question that we want is what is the function? Suppose your friend wants to associate the function phi tilde of y. Okay? He wants to write what phi tilde of y is. But what the number as a function of his y coordinate is. What is that? And the answer is, of course, phi tilde of y is equal to phi of x of y. So that at the same space-time point, you get the same value. This looks a bit trivial. It's not at all trivial. You know, just as functions, these are different. And one must keep this in mind all through. So we're going to be doing field theory. So we're going to be studying functions of position. And coordinate transformations change these functions in the way so as to keep the value of this field same at the same space-time point. But as functions of coordinates, they're different. Okay? Fine. So this is the first thing that we have. Okay. Now, let's look at something a little more complicated. Suppose you were interested in the derivative of your function. Okay. So, you decided to look at the field del mu phi. And I'll be a little more explicit. Let me say, because we're working partial derivative, keeping all other x's constant. Okay. This thing gives us four new functions of space-time. Okay. Now you might ask, your friend might say, okay, this guy thinks he's smart, but I can do the same. I can make del by del y mu of phi tilde of y. Okay. These are my functions as good as your functions. Fine. The question we want to ask is, knowing one, how do we get to the other? Okay. So, for scalars, we found the formula. What is the equivalent formula for these derivatives? So you can say, look, I know that phi tilde of y was equal to phi of x of y. Okay? by del y of phi of x of y. Well, what is that? By the chain rule is equal to del by del y mu of x mu times del by del x mu of phi of x. And then once we've got this, we've taken the derivative, we start substituting x equals to x of y. Because we want the answer to be a function of y. Okay? But in taking the derivative, we regard this as a function of x. Now, so let me give this guy a name. Let me call this object a mu of x. Let me call this object a tilde mu. This quantity here is a tilde mu of y. So what we've derived is that a tilde mu of y is equal to del x mu by del y mu into a mu of x. Is this quantity a? Okay? So now, in this change of, in this dictionary element, there are two things. There is the fact that the argument has changed, as we see here. That's the same as in the scalar function. But there's something new. There were indices of these functions, and they get mixed around linearly. Okay? So this is how derivatives of scalar functions transform under coordinate changes. Is the scalar. Okay? Because we'll have use for it later on, I'm going to actually just work this out for a special case. The special case that the coordinate change is an infinitesimal change. Okay? So suppose x mu was equal to y mu plus epsilon mu of y. And we're going to work the first order next. Okay? Then what does this formula become? In that case, where do we get two terms? First, we get the term from here. And in this part. Okay, so saying a tilde mu of y minus a mu of y is equal to, and let me write it down, and you see you agree. The first term is epsilon dot del into a mu of y, and then the second term is plus del epsilon mu by del y mu into a mu. Okay, to first order an epsilon, this is how the function a tilde of y is different from the function a of y. A mistake that is very common to make when you first studying these things, because textbooks sometimes say this so badly, is to keep this term, but to forget this term. Just as differences in function. This came from expanding the dependence in the coordinate. You must remember that that's also there. As differences in functions, there's the term that exists even for scalars. You know, people often say scalars are invariant, but as functions they're not the same. That's very important to keep in mind. Okay? And these two terms, you know, appear the same foot. Okay, excellent. So that's how derivatives of scalar fields transform. Now, we're going to make a definition. Okay? Any object that transforms in this way, according to the law for transformation of derivatives, any object that transforms in that manner is referred to as a contravariant vector and a tensor with one index down. Go ahead.
So these A tilde and A, they are evaluated on the same space-time point or?
You've got a function A of A. Everything's evaluated in the same physical point.
Same physical. So it should be A tilde mu y minus A mu x, right?
No. We've expanded out that difference. Now, in this difference, we're not evaluating in the same space-time.
We're not calculating on the same space.
We are looking at the difference between the two functions.
Okay, two functions have the same values of y.
Yes, the same value of argument. Okay, that's the reason we got this. Okay, yeah. Excellent. Okay, so let us continue. So, covariant, right? Index down. Okay, right. So, any object that transforms like a derivative is called the covariant vector. Okay. Now, there's another kind of object that will be of interest to us. And the prototype of this kind of object is the infinitesimal displacement, dx. So what do I mean by this? Look, I've got my manifold here. I've got a point. And I take at each point, I draw a little vector. By which I mean draw a little arrow on my manifold. Very little, infinitesimal. Okay? That infinitesimal object I choose differently at different points in space. Who can stop me from doing this? So I do it. So I've got what I'm going to call a vector field of these little arrows as a function of where I am in space. Okay? But you know, your friend who likes the y coordinates very competitively says, you draw these arrows, I'll draw my own arrows. So he draws dy mu of y alpha. Okay? And what we want to know is, how do we go from your description to your friend's description or vice versa? For these little arrows that we've drawn all over space. Okay? Is this clear? Is this dx mu clear? Dx mu is just the difference in coordinates between the tip of the arrow and the base of the arrow, where this arrow is infinitesimal. And is chosen completely arbitrary as an arbitrary function of space. So what we will later on call the vector field. Okay. Something with this is going to have an index up. See? And indices up are called vectors. Okay. This is a vector field in space. What I'm trying to understand is what is the law of transformations for vector fields. Okay. So now let's say it's very easy for the following reason. So what we know is that that x is equal to x of y. Okay, so we plug that into here. So we get dx mu is equal to dx mu del x mu by del y alpha in a dy alpha. Okay, so this was at position x. I'm going to make everything as a function of y. Of y. So in order to get what your friend wants, what your friend should do, we have to invert this relation. Now, the inverse of this matrix is the other one. Now I'm going to ask somebody to prove it to me, but I just use it for. So dx mu of y is equal to del y mu by del x alpha dx alpha of x. But I've used the fact that del x by del y, the matrix del x by del y, is the inverse of the matrix del y by del x. Okay, so let's not waste that. Okay. The fact that these two matrices are the inverses of each other, you probably know. But anyway, it's obvious from the following observation. If you write dx mu is equal to del x mu by del y alpha e y alpha. So you can also write dy alpha is equal to del y alpha by del x theta dx theta. Then plug into each. Okay, so take this relation, plug in here. We have to get dy alpha as dy alpha. But that's the product of these two matrices, so they must be matrices. Okay? Fine. Okay. That's the cardinal state of teaching. You never know how to write it. Sorry. Okay. Sorry about that. Okay. Now, fine. Now, any object that transforms according to this transformation rule is called a vector field. And what is the transformation rule? Just to write it down once clearly. The transformation rule is A tilde mu of y, your friend's vector field, is dy mu by dx alpha A alpha of x field. Now, there is something about this transformation rule that is less natural than the transformation rule for the object with one index down. And that thing is this. Look, we are so far saying that you had a function x as a function of y. In the rule for objects down, everything that we used is just that function x as a function of y. Okay? This derivative computed if you know x is a function of y. And this dependence is clear if you know x is a function of y. Here, we need y as a function of x to take this derivative. This is x as a function of y. But this involves y as a function of x. Now, as long as you take a coordinate change, which is invertible, that's fine. And through much of our discussion, we'll assume this. However, there are some situations in which you want to go, in which and we will be dealing with this soon, in which you're interested in some sort of submanifold of order spacetime. And let's say that the y coordinates label positions of that submanifold. Okay? Then, this formula still makes sense. But this one doesn't. Okay? What we concluded is that given a one form, an object with one index down, it leads to a natural formula for a one form on submanifolds. An object with one index down on submanifolds. But the same thing is not true for vector fields. Okay? This is a throwaway comment. If it's confusing you, forget about it. We'll come back to it when we need it. Okay? The reason is because the vector field may have a component that's not in your submanifold. Then you have to determine a rule for projection. And that involves more information than what we got. Okay? But one forms naturally descend. Under some this descension has a fancy name in mathematics called a pullback. It's a nice thing. Pullback. Okay, good. Fine. So far we've understood. So that was a throwaway comment. Don't let it confuse you. Okay, it's confusing. Forget about it. Okay. So far what we've done is determine the rules for transformation of vector indices and these other things, these downstairs indices, covariant, whatever they call the downstairs indices, form indices. Okay. Now I'm going to make a definition. Look, as we will see in the study of general relativity, we will need vector fields. We will need one form of fields. But we will need many different kinds of fields. Arbitrary, what we're going to call arbitrary tensor fields. So, an object A with indices a mu1 to mu n, nu1 to nu n as a function of x is called a tensor field. It has some name, but let's just call it with n upper and n lower indices. With n upper and n lower indices, provided that the rule for coordinate transformation of this tensor field is given by, let's write it down. The rule for coordinate transformation is given by a tilde of y, let's call it alpha 1 to alpha n, beta 1 to beta m, is equal to del y alpha 1 del let's call it del x mu 1 del y alpha n del x mu n, and then del x del y nu 1 and no, this will be called beta 1 and nu 1 del x nu m del y beta m, and now I'm going to rub this out. Okay, multiplying a of mu 1 to mu n nu 1 to nu m of x of y. Okay, so that's a bit of a mouthful. But provided this field obeys this transformation rule, we call the field a tensor field with the n upper and n lower indices. As you can see, what we've done basically is give one factor of this transformation matrix for every upper index, and one factor of this transformation index for every lower index. So in particular, if we had just one lower index, we'd recover the one form transformation rule that we have done before. If we had just one upper index, we'd recover the vector transformation rule we've done before. But this is the natural generalization to now with recent indices. Okay? In particular, if you've got a product of two vector fields, then they will transform as a tensor with two upper indices. Can you see this? Could someone? How would you prove this to me if I asked you to? What would you do? Just tell me the steps. It's totally obvious, I agree, but just to hear you say. And let me say, so what you would do is just take a tilde of the first vector field, right, in terms of a of the first vector field. A tilde of the second vector field, right, in terms of the second vector field. Each of these transformations has one factor of this del y by del x. So you in general get two factors of del y by del x multiplying the product. Okay? So this rule is generated so as to ensure that products of tensor fields are tensor fields with the indices just added. Okay? You take a product of a vector field and a one form field, you will get a tensor whose index with one index up to one index down. Okay, according to this definition. Yes?
Is the converse true means all tensor fields can they be represented as the products of vectors and one-forms?
Okay. As sums of products of tensors, but not a product. Let me ask you this question about matrices. Okay? Any matrix can be thought of as an outer product of a row and a column. I mean, sorry, an outer product of a row and a column is a matrix. Can every matrix be thought of? Clearly not, right? Because only matrices of rank 1 can be thought of that way. But anything can be thought of as a sum of such things. Okay. Good. Other questions, comments? Excellent. Oh, wait. Yes?
So in the case of we are dealing with as he said, that the determinant G is -1.
Yes.
So general coordinate transformations are not.
Well, not -1.
I mean,
It's a negative.
negative. So I mean, if you're doing a general coordinate transformation,
Yes.
then the Jacobian should be positive.
Yes. The Jacobian should be positive. You see, no. You see, the determinant transforms with two factors. Okay. All we require is that the coordinate transformation is 1 to 1, where the positive negative should not have that. Fine. Other questions about this? Okay, we're almost near the end of our time. Give me one more. Okay. I should just clear. Okay. The last thing I should say is that with these rules, let me say 2, 3 quick things. Firstly, with these rules, the object. Okay. This is how we define tensors. Now, there are interesting objects which are called invariant tensors. The invariant tensor has the property that as a field, it takes the same functional form in every coordinate system. Okay? Any tensor in one coordinate system can be transformed to another coordinate system. Nothing special. But, as we've seen, for instance, in the infinitesimal transformation law for the vector field, or for the one guy downstairs, the one form field, the nature of the field, the functions in mu of x change when you do this coordinate transformation. Right? Now, suppose you've got a field, some sort of tensor field, such that you get the same functions of x as you had functions of y. Such an object is called an invariant tensor field. Okay? That is, that you do the coordinate transformation property, and then the answer as functions is the same. Okay? Now I emphasize this as functions, so the simple examples will have trivial dependence. Let me give you an example. Suppose I take the object, this object. So a field, a tensor field T alpha nu, which is this. It's a Kronecker delta. So it's always either 0 or 1. And it's 1 only when the two is 3. Now, let us find the rule for the transformed Kronecker delta. Okay? So this was the tensor field in your coordinate system. And your friend's thinks this is a cool tensor. He wants to know what he should use in order to get your Kronecker delta. Okay? So, he says, well, that's easy, I have this transformation law. So let me apply it. Okay. Now, part of this transformation law is trivial because the x of y business is trivial because it's not a function of x. So we just have to worry about this part. So what we get t tilde of, let's apply this, alpha beta is equal to del y alpha by del x mu delta mu del x nu by del y beta nu. That's what the transformation rule gives us. Okay, so the thing that he will get by transforming your tensor field to his coordinate system is this. Okay, but now delta mu nu just identifies indices. So it tells you that these indices should be identified in some. But that means multiplication like a matrix. But we've already seen that these two are inverses of each other for a matrix function. So this is delta alpha. So, if your friend takes your tensor field, and applies the transformation rule, which was this, applies the transformation rule onto it, he gets a tensor field which has the same rule in his coordinate system. Okay? So the tensor field in his coordinate system is the same, but given by the same formula as function of coordinates. In this case, of course, trivial coordinates. As was true in your case. Such a thing is called an invariant tensor field. Okay? Now, so this is a nice invariant tensor field, the tensor field, Kronecker delta. But that is invariant actually is also clear from the fact that A mu is equal to delta mu A mu. This equation is true in every coordinate system. Since this transforms like a vector, this transforms like a vector, and the coordinate transform, there's a better transform like a tensor. Given something of which I forgot to say something. The second thing, and this is really important, is that if you take an upper index and a lower index and set those equal, identify them and sum over all values. So I take, let's say I've got a one form and I've got a vector field. A mu is a vector field, theta mu is, A mu is a one form field, theta mu is a vector field. Now I form the following object. I form the object sum over mu, A mu, theta. Okay? I ask, how does this transform? Answer, it transforms like a scalar. Like a scalar field. Proof. Okay? A tilde mu is equal to del y mu del x. So theta, A theta of x of y. A theta tilde mu is equal to del y mu by del x of beta. Theta beta of x of y. Now I multiply these two, put them in here. So what I've got is, since these mu's are equal in here and summed over everything, and just sum over this index here, then I use the fact that these two are inverses of each other. So I get a factor of delta theta beta. So we conclude that A tilde mu theta tilde mu is equal to sum over mu is equal to sum over, let's say, theta A theta of x y theta of y. So then we said, look, we were interested in Lagrangian to describe the free motion of a particle. Let's say that the coordinates of that particle were x dot. I'm sorry, were x and x dot is its velocities. Okay? Since we wanted translational invariance for free motion, our Lagrangian had to be a function of x dot. In general, Lagrangian is a function of x and x dot, but translational invariance requires this particular Lagrangian to be a function of x dot. Then we wanted rotational invariance, so this thing was going to be a function of x dot dot x dot squared. So then we said, well, the most general Lagrangian would be some function of x dot times x dot. Okay? Now, translation invariance, rotational invariance all satisfy that such a Lagrangian. But this leaves a lot of freedom of whole function. F of a real variable, that wasn't good enough. Then we applied the Galilean principle. We wanted this Lagrangian to be invariant up to possible total derivative terms under Galilean boosts. That is, x dot goes to x dot plus constant. Well, you remember, under x dot goes to x dot plus a constant. Okay, let's make this constant infinitesimal. Okay, so let's go. This Lagrangian transforms how? Well, clearly the change in the Lagrangian, let's look at the change in the action. So delta S, which is equal to integral delta L, is equal to f prime of x dot squared times the change in x dot squared, which is x dot times dot epsilon. again, this is probably a factor. Okay. Now this guy in general is nothing nice. But if f prime of x dot was a constant, then this is a total derivative. That's the dot and x dot. Okay? And that we argued was more or less the only situation in which it would be, for arbitrary motion, would be a total derivative. Okay? So that tells us that f prime of x dot squared had to be a constant. We call the constant was related to what we call the mass of the particle. So that told us that f was a linear function at x dot. The constant part was irrelevant. So we concluded from that the Lagrangian of free motion was m x dot squared by 2. Okay, great. Now in this course, we're going to be interested in motion of things in a relativistic setting. So the first question I'm going to ask is, what is the motion of a free particle what is the Lagrangian for the motion of a free particle within the theory of special relativity? I'm going to address, I reminded you of this because I'm going to address the question in an entirely similar way. Okay, so as before, we want write your name and email address on the sheet, pass it on to Umesh, who, as the classical mechanics people know, is the tutor. Continues to be the tutor for this course. Okay, and we'll start an email list to Umesh, and so any practical issues we'll discuss over email. By the way, are the lecture timings okay? Okay, this slot and Thursday in the afternoon. Now there's one small problem. This room may or may not be available Thursday afternoon. There's some confusion regarding that. If it's not available, we'll send you guys an email telling you where Thursday's is. Okay. Fine. So let me just continue. So the Newtonian theory of gravity, which was approximately correct, sounds at the very least ambiguous given the formulation of Chekhov's special relativity. Okay. For instance, as we said, the question is distance in which frame. Another question is, does it sound really reasonable that you've got a force which is sort of like electromagnetism, but it has no analog of magnetism? There is no analog of forces that are affected by the motion of the motion of your masses. None of this sounds like it's likely to be able to be made consistent with the principle of special relativity. Okay, so Einstein was led to search for a better theory of gravitation, a theory of gravitation that would be consistent with the principles of special relativity, for obvious reasons. You know special relativity is correct. You've got experimental evidence for that. It's a nice theoretical framework. Gravity is correct. Okay, you've got experimental evidence for that. There's experimental evidence for that. Okay, gravity exists. You need a theory that makes the two consistent. And Einstein set about trying to find such a theory. And in doing so, Einstein realized that he had to modify, or maybe more accurately, enlarge the theoretical framework of special relativity and come up with an entirely new theory of gravitation. Not something that takes Newton's laws and tweaks it a bit, but come up with an entirely new theory of gravitation, a theory of gravitation that has that is qualitatively different from Newton's theory in the sense that it has phenomena that are qualitatively new phenomena that are not present in Newton's theory. For instance, in the theory of electromagnetism, which governs the interaction between two charges, there's a force that governs the interaction between two charges, but there are also excitations carried by the force field. There are waves, electromagnetic waves. In Newton's theory of gravity, there's nothing like that. Yes. Force between two objects. The correct theory of gravity that we will study in this course. So this course is is on Einstein's general theory of relativity, which remains almost 100 years after it was invented, the best classical theory of gravity we have. Okay, so thanks. So the point of this course is manifold, and the most basic level what we want to understand is the theory of gravity. We want to understand the force of gravity. Okay, the force of gravity. We know something about it. Newton's laws of gravitation govern gravitational motion in an approximate sense. A lot of you are very well familiar with the Newtonian theory of gravity. However, Newton's theory of gravity is not quite correct. It was a beautiful theory and has a large range of validity. I mean, doing calculations for rocket motion in the solar system, unless you're interested in real precision, you might well use Newtonian gravity. But it's not completely correct. It's not completely correct as has now been seen in many ways from experiment. And its lack of correctness is also clear. Given Einstein's special theory of relativity. If we believe the relativity principle is correct, that already makes the Newtonian theory of gravity sort of already ambiguous. Because, for instance, the law of universal attraction, which tells you that the force between two objects is inversely proportional to the square of the distance between the two objects. You could ask square of the distance in which frame? Or square of the distance, measured along what line of sight will take, which is more or less a question. Okay? Then you could also ask, is it true or is it plausible? Is it true? Okay, so this is getting too crowded. What do we do about this? So, yeah, there are a couple of seats in front, so please, 2 people at least come in. I have the suspicion that this that this is a first-class crowd. So we'll try to avoid moving the class to a bigger room. We'll do it if 3 classes down the road we still have a crunch of space. Okay. Okay. Great. Okay. Yeah. So maybe actually there are very practical things I should have mentioned before. Start. So relative power that then has been successfully tested by zillions of experiments. Okay, so it's in the way that it's a theory that sort of that allowed itself to be deduced by very little information, just by following deductive logic, and then allowed the description of a wide variety of physical phenomena, including evolution of the universe. We'll see some of this. Of course, it's really, in some sense, a paradigm for great physics, for great theoretical physics, at least for some of us. It's like a great intellectual victory for humanity to be able to do this. Okay, and for physicists of my inclination, string theorists, it's the inspiration to hope that other great contradictions in physics, meaning the apparent mismatch between quantum mechanics and gravity, for instance, could also lead to beautiful new results that have a large number of experimental predictions, but guided largely by formal, by structural theoretical considerations. Okay, so I feel that. So I said all this because I feel that the study of general relativity is important, both because it's a beautiful theory of nature that describes a wide variety of phenomena in nature, but also as a paradigmatic, as the example of perhaps what I think is the best theory of physics. It's the most beautiful theory of physics. Okay, so just as an example of, if you're going to try in your career to make a good theory of physics, hold this up as an example. Okay, if you can do it, if you can smash Einstein, you've done it. Okay, great. So, fine. So now that we've had this introductory spiel, let's start the course. Okay, so I'm going to start the course by reminding you of something we discussed when discussing classical mechanics. Many of you took classical mechanics course last year, and we started our discussion of classical mechanics by saying that, look, we're going to assume that classical motion, the motion of classical particles, this is governed by Lagrange. And we were also going to assume that this Lagrangian was a function only of positions in velocities, so that the equation of motion would be at most second order time derivatives. Okay? And the first thing we tried to do in that course was to try to understand what Lagrangian governed free motion of a particle. Okay? And in order to try to do that, we assumed the principle of Galilean invariance. That is, that two observers that were related to each other by constant velocities saw the same laws of the equation of motion. We use the same Lagrangian to describe equation of motion, to describe in particular free motion. Okay. So, as waves includes waves just like electromagnetic waves, waves of the force field carrier of gravitation, which are called gravitational waves. Okay? And this is a consequence of Einstein's theory. Okay, so Einstein's theory of gravity modifies Newton's theory in some ways, but also gives you qualitatively new phenomena. Okay, so the first motivation for studying general relativity is to find the correct theory of gravity. Okay, but now suppose you're a statistical physicist who feels he is unlikely to encounter strong gravitational effects. Maybe you've got, say you're a biophysicist. I don't know, but a physicist is not particularly likely to encounter strong gravitational effects. And you might think, well, that there is a modification of the laws of gravity in slightly strange circumstances, not of great relevance to me. So, for me, why should I study Einstein's theory of relativity? Okay? I personally feel that there's good motivation for every physicist to study Einstein's theory of relativity. And let me tell you why I think so. I think Einstein's theory is a paradigm for good physical theories. It is a theory that, as I mentioned, was invented in order to resolve contradiction between two different elements of known structures of physics. And just by the desire to resolve this contradiction, Einstein, through 10 years of intense and frustrating labor, was eventually led to a new framework that does many things, completely overturns many of the conceptual underpinnings of earlier classical theories of physics, that predicts a wide host of new phenomena. Okay? And that has a great degree of theoretical elegance and beauty. It's a theory with no parameters or no new parameters. Predicts a wide range of new phenomena, has a large amount, makes contact with beautiful mathematics. It's a really beautiful theory. And was invented purely with the desire, from starting with the conviction that there must be a way of overcoming the apparent contradiction between two theoretical notions, both of which are known to be grounded in reality. Okay. What I want to emphasize here is that almost, as far as I'm aware, almost uniquely in the history of physics of this high level, the invention of general relativity was guided by experimenting in very limited way. Einstein, of course, knew that there was gravity. He knew that special relativity was gravity. But he wasn't trying to fit the data of a particular experiment or a class of experiments. He was trying to find consistency of theoretical structures. And in doing that, he came upon a new theory of stupendous beauty, but also enormous predictability.